Okay, so let's sort of summarize here, because we basically have a situation where we have this impermeable phospholipid bilayer, right, that separates the inside of the cell from the outside of the cell. But there are a number of proteins, right, that allow for the passage of ions. Some of them are ungated when they let, potassium flow out of the neuron, right, because the concentration gradient force, right, the movement from high areas of concentration to low sort of wins out over the electrical force in the case of potassium at the resting potential, right? So potassium tends to flow out. Sodium, right, is sort of masked on the outside of our membrane, right? Wanting to come in, it's been sort of sent there via the sodium-potassium pump, right? And the fact that the membrane's not very permeable to the passage of sodium, right, in a neuron at rest. We can actually measure, though, the value of the resting potential. And again, I want you to think about that's the difference in charge, inside of the membrane versus the outside, in a neuron that's not sending a current, that's not sending what we call an action potential from one end to the other. So this is a neuron at rest, right? Inside the cell, we have more potassium, right? I want you to think about the reasons why. The pump is bringing potassium in, right? Pump keeps bringing it in. We have far less sodium. Think about why. Because the pump is kicking sodium out, and the membrane's not very permeable to sodium. It's hard for it to get back in, right? And there are more anions. Remember, these are proteins that tend to be negatively charged. Why do we have more of them inside than out? Well, because they're manufactured inside. They're big, right? Unless there's some sort of special conduit or pore or channel to allow them to pass through the membrane, they're going to stay inside and add additional negativity or negative gas to the inside of the cell. Outside the cell, we have less potassium. Why do we have less potassium? Because the pump continues to bring potassium in and establish a higher concentration inside versus out. We have a lot more sodium. Why do we have a lot more sodium on the outside? Well, because the pump is kicking sodium out, and again, the membrane of the neuron is not particularly permeable to sodium, right? And we have fewer anions or proteins. Why? Because they're manufactured on the inside, and it's difficult for them to leave the cell, right? You don't want them to leave the cell. That usually means there's been some sort of damage to the cell, right? So if we were to compare the intracellular and the extracellular fluid, right? And we could do this. If you have a separation of charge, if you have a difference in charge so that the inside is more negative, right, than the outside, if you allow some kind of conductor, if you introduce a conductor into the cell and have the other end of the conductor on the outside of the cell, that difference in charge will provoke the flow of a current, right? A current will move, right, from one, location to another. So if we take a little, scope here, right, and we, take an electrode, this is a piece of metal, we jam it, through the membrane into the intracellular space, right, where it's more negative, and we have another one out here, or another electrode in the extracellular space, current will start to flow. And we can, put a little set of units, on how much current, to give us a sense of how much force is being exerted as that current flows, how much current is going to be flowing, right? And we can measure the force of that current in what's called volts or voltage. And your brain generates electricity, neurons generate electricity, but they're relatively small, units or small amounts of electricity. We call them millivolt. They're measured in millivolts, which are thousandths of a volt, right? So the difference in charge between the inside and the outside of a cell is actually at rest about minus 65 millivolts. That just means it's a relative measure that the inside is more negative than the outside. By how much? By about 65 millivolts. It's more negative inside versus the out. So the resting potential we describe as minus 65, and I write here a range because there is a range. It'll depend upon the species. It'll depend upon the part of the brain. It goes from minus 65 to about minus 70 millivolts. That is the resting potential.